This is a review of fluids for AP Physics 2. When we studied fluids, we said that matter exists primarily in three phases: solids, liquids, and gases. And that while solids don't flow, liquids and gases do. And so when we studied fluids, we were studying the properties of primarily liquids, but liquids and gases. And that's because both of those states of matter flow, and that's our definition of what a fluid is. So as long as something flows, then it can be called a fluid. And when we studied fluids, we studied properties like pressure, volume, density, and speed. Because sometimes it's more convenient to talk about the pressure or volume of a fluid than it is to talk about the mass of the fluid, for example. One important property of a fluid is its density. And density is written as the Greek letter rho. So it's not a P, it's a Greek letter rho. And we know that density is mass per unit volume, or mass divided by volume, where the mass should be measured in kilograms and the volume should be measured in meters cubed. And when those units are used, the density of water is 1,000 kilograms per meter cubed. One reason why density is important is because if I have a little bit of water or a lot of water, the density will be the same. So it's a property that's unique to each substance. It can be used to identify the substance, and when we're considering fluids, sometimes we have more or less amounts of fluid, and so it's important to have a property that doesn't change with amount like that. Also, it's important to recognize that the mass of a fluid could be expressed as its density times its volume. Another important property of a fluid is its pressure, which is represented by a capital letter P. Pressure is a force per unit area, so if forces are measured in newtons and areas are measured in meters squared, then pressures have units of newtons per meter squared. And one unit that we use to describe pressures is a pascal. 1 pascal is equal to 1 newton per meter squared. And so as long as you're using SI units, pressures should be written with units of pascals. Similarly to expressing the mass of a fluid as its density times its volume, the force exerted by a fluid could be expressed as the pressure it exerts over the area, so the pressure times the area. The atmosphere, so at sea level, the atmosphere exerts a certain pressure, and that pressure is typically represented with the symbol P naught, or at least it is on our equation sheet. And atmospheric pressure is 1 times 10 to the 5 pascals, which is also redefined as the unit of 1 atmosphere, or 101.3 kilopascals. All three of those units are important. They're all equivalent measurements of atmospheric pressure. We know that, as my picture shows in the top right, that pressure is generated from particles of a fluid smashing against the walls of a container. But if we look more closely at each individual particle, we can see how they exert a force on the walls of the container. So in the picture at the bottom, I have a velocity, a particle with a mass, lowercase letter m, that has a velocity that's down and to the right, that's shown in red. Part of its velocity is perpendicular to the surface and points downward, that's shown in green, and part of its velocity is parallel to the surface to the right. After the particle collides with the surface that I have drawn below, it will bounce up and go to the right. The parallel velocity still points to the right in blue, but now the perpendicular velocity points upwards. So there was a collision between the particle and the surface, and when that collision occurred, the wall applied an upwards force on the particle, and the particle applied an equal downwards force on the surface of the container. And that's why the direction of the velocity, or that perpendicular velocity, changes for the particle. And so we could express the force that the particle exerts on the wall and the force that the wall exerts on the particle using Newton's second law. And so F equals ma, and the acceleration could be rewritten as a change in velocity over a change in time. If I define the upwards direction to be positive, then in this equation where I have delta v written, that would be the final velocity minus the initial velocity. The final velocity, that perpendicular velocity, points upwards, and so it should be positive. And the initial velocity points downward, so it should be negative. So I should have v minus negative v. And so in colliding with the surface, if that collision happens in an amount of time delta t, then the force that gets exerted is 2 times the mass of the particle times its velocity perpendicular to the surface divided by delta t. And so if I wanted to know the pressure generated by one collision from one particle, it would be that force divided by the area over which this occurs. Or more logically, it would make sense to talk about a large number of particles, which would typically be represented by a capital letter N, and say that each particle is exerting this force of 2 mv divided by delta t, and there are n, capital letter N, number of particles. So the total force would be n times this expression for the force, and the area would probably be the total area of the surface of the container. As we studied pressure, and we looked at the pressure at different points in a fluid, we found that for a fluid with a given density, so all fluids of the same type will have the same density, in a place where the gravity is equal to g, the pressure depends only on the depth. So pressure and depth, there's a relationship there. So up above I have 3 different containers that have wildly different shapes, and if they were filled with fluids up to the top, then the pressure at h1 and a depth of h1 in each of those containers would be the same. The pressure at h2 in each one of those containers would be the same, and at h3 the pressure at each one of those containers would be the same. And that's because despite there being different amounts of fluids, there's a complicated relationship with at a particular depth, the fluid there has to support the weight of all the fluid above it. But in cases where there's more fluid above it, like in the container on the right-hand side where it's wider at the top, the walls also play a role in supporting some of that extra fluid. And so the only thing we need to remember is that at a given depth, regardless of the shape of the container, the pressure will be the same. But we also know that above the container, there is atmospheric pressure pushing down on the fluid. And so if you want to actually know the true pressure, the total pressure at any given depth in a fluid, that would be given by the equation that's at the bottom, not the one that's in the middle. So the pressure at a particular location in a fluid would be equal to the atmospheric pressure above the container of the fluid plus the additional pressure due to the weight of the fluid because of its depth. Continuing along with this discussion of equal pressures at equal depths, if we look at what happens when we put a fluid into a U-shaped tube, on the left-hand side, I've just filled with the tube with a fluid that's the same everywhere. And because the atmospheric pressure pushing down on one end of the tube is the same as the atmospheric pressure pushing down on the other end of the tube, the fluid will rise to the same heights on both sides of the container, and that's because they have to equalize the pressures that are at the bottom. But since the fluid is the same everywhere, the density of the fluid is the same everywhere, and the pressure is the same everywhere. So the heights are the same. If I pour different fluids with different densities into the two sides of the tube, then the heights on the two sides of the tubes won't be equal. And that's because the fundamental thing that needs to be balanced is not the heights, it's the pressure at the different depths in the fluids. And so while the atmospheric pressure pushing at the top of each fluid through those open ends is still the same, for a material that has a greater density, the pressure will increase at a greater rate, or at least the pressure will be greater at a given depth. And so in order to create equal pressures at the bottom of the tubes, the fluid that has the smaller pressure, in this case the yellow fluid, will have to rise to a greater height in order to create the same pressure at the bottom of the tube. And so that's why in this picture I've drawn this height to be greater than this height, because at the top I've indicated that the density of the green fluid is greater. And so you don't have to go as far into the green fluid to get that greater pressure. And so there's a greater stack or weight of fluid that has to be created on the left-hand side to create that equal pressure on the bottom. We also saw a demonstration where I had a large container of fluid which had a small tube connected to it. And this is being shown on the right. And despite it not being incredibly intuitive, the height of the fluid in that very narrow section of the container on the right and the height of the fluid on the very wide section of the container on the left is the same. The weight of the fluid on the left is obviously much more than the weight of the fluid on the right, but it rises to equal heights because this is a connected fluid, and in that connected fluid all throughout the bottom there, the pressure of the fluid has to be equal. And the way that is created is by having the fluid rise to equal heights on either side of the container. Another topic we studied when we studied fluids was Archimedes' principle. Fluids exert an upward buoyant force on objects because when I place an object into a fluid, if it starts to get submerged into the fluid, then we know as the bottom of that object goes down into the fluid, it would be experiencing a greater pressure than the top. So in the picture that I've drawn, an object is partially submerged into a fluid. At the bottom of that object, the pressure would be the atmospheric pressure at the top plus the additional pressure due to the depth that the object has reached into the fluid. And at the top, it would just be the atmospheric pressure. So if I can express the force exerted by the fluid as the pressure times the area, then the upwards force due to the pressure at the bottom of the object would be equal to the total pressure of P naught plus rho GH times the area of the bottom of that object. And the downwards force caused by the atmosphere pushing down on the top of the object would be the pressure at the top, which is atmospheric pressure, or P naught, times A. And because of this fact, there is an upwards force. You could imagine subtracting those two force vectors that points upwards. And that's what we call the buoyant force. Now, in this picture that I've drawn, mg also points downward, and that's what causes the object to stay at rest there. So the upwards buoyant force and the downward gravitational force causes an object to be at rest for an object that is floating. But this buoyant force that I've drawn here, and it really is the force that keeps the object buoyant, is equal to the weight of the fluid that is displaced. The weight of the fluid, right? So when I write my expression for the buoyant force, Fb, rho represents the density of the fluid, v is the volume of the fluid, and g is gravity, or 9.8 meters per second squared. And again, as I mentioned previously, rho times v, the density times the volume, is the same as m, the mass of the fluid. And so you could also think of this equation as being, mg, where m is the mass of the fluid displaced. And that's why the buoyant force is equal to the weight of the fluid displaced. So for an object that's floating, the buoyant force points up, and we could represent that in a free body diagram as Fb, and the weight of the object points down. And if it's floating, then those two forces are equal. It's good now to talk about what would cause an object to float or sink. An object will float if it's less dense than the fluid. And so in this example, if my object has a density that is less than the fluid it's being placed in, then it's going to float. And if that happens, just as I mentioned, the buoyant force that points up will be equal to the weight of the object that points down. If an object has a density that is greater than the fluid it's being placed in, then it could sink, in which case the weight of the object that points down would be greater than the buoyant force that points up. Therefore, we can't really do as many calculations for that case because we don't know if it's just a little bit more dense than the water or if it's much more dense than the water. Regardless, it'll sink, and so we can't relate the buoyant force to the weight as we can when it floats, where there's more of a state of equilibrium. But one thing that is important for an object that is totally submerged is that when an object is submerged, the volume of the displaced water, which would be used in the buoyancy force equation, is equal to the volume of the object. And that's not true when it's floating. An object doesn't displace a volume equal to its own size when it's floating because part of the object is above the water. And so bottom line, when I place an object into water, due to the densities, an object will displace enough water so that way those forces are equal, or it will sink. Also, it's important to realize that if the densities of the two objects are very close, or if they're equal, then it's possible for an object to be somewhere within the fluid and be at a state of equilibrium where it's just floating in the fluid. It's not at the bottom and it's not at the top, it's just somewhere within the fluid. So far we've been discussing mostly fluid statics, so fluids that are at rest. Fluid dynamics talks about fluid flow. If I have a fluid that's moving through a pipe like I have drawn on the top left, then the size of the pipe, the area of the pipe could change. And we learned about something that was called the continuity equation. The continuity equation relates the area of the pipe to the speed of the fluid, where the area would be in meters squared and the speed would be in meters per second. And we learned that if the area gets bigger, then the speed goes down. Or if the area gets smaller, the speed goes up. So there's an inverse relationship. The areas, if the pipe is cylindrical, could be given by pi r squared. And so it's important to remember that if in a problem I'm given the diameter of the pipe, that I need to find the radius and then remember that the area is proportional to the square of the radius, and then subsequently use that in my calculations. One of the reasons why we can prove that a fluid will actually slow down if the area gets bigger or speed up if the area of the pipe gets smaller is by Bernoulli's theorem, which says that when a fluid reaches a narrow constriction, the velocity increases and the pressure decreases. So in this second pipe that I have drawn, the pressure on the left-hand side of the pipe would be bigger, and the pressure on the right-hand side of the pipe would be smaller. So we're explaining why, as the area drops off and becomes smaller, the velocity increases. And this is because what we call the back pressure, the pressure on the left-hand side of this pipe would be greater, and that greater pressure on the left-hand side of the pipe causes a force to be exerted on the water in the more narrow section of the pipe. That force causes an increase in the speed of the fluid. It actually accelerates as it moves from the bigger section to the smaller section. So that back pressure is what's causing the fluid to speed up in the more narrow section of the pipe. Of course, we know now that Bernoulli's theorem can also be expressed as an equation. And this equation is essentially the conservation of energy equation for a fluid. And so if I have the most generic case where at position 1 there is a large area a certain speed, a certain pressure, a certain density. And then at position 2, I have a different area for the pipe, which will correspond to a different speed, and the pipe is even at a different height than what it was at position 1. Then we can relate these two positions by Bernoulli's equation, which says that P1, which is the pressure at location 1, plus rho g y1, and rho represents the density of the fluid, and the density is something that is the same at positions 1 and 2, and that's why it wasn't labeled with a subscript. G is the same at both locations, but the two vertical locations of the pipe are not the same, so that's why this first position is labeled as y1. And then the last term for the first location is 1/2 times the density times the speed at that location squared. And you might remember that this first term represents the pressure, but the second term is very similar to potential energy, and this third term is very similar to the kinetic energy. And similarly, there is a pressure term, a potential energy term, and a kinetic energy term for the second location. And at location 1, it corresponds to a high pressure and a low speed, and at location 2 it corresponds to a low pressure and a high speed. And so there are differences between location 1 and 2, and energy is conserved between 1 and 2 due to the conservation of the flow of the fluid. One of the things that's pretty important to remember here is that we will typically define one of the positions, maybe the bottom one, as being 0, which tends to cause one of the terms in this equation to drop out. And so we can cross off this term when we were solving a problem. Also, it's important to remember, to sort of tie all these concepts together, that in the picture that I have drawn, the pressure at location number 1 would be greater than the pressure at location number 2 because the pipe is bigger. So of course, that bigger pressure at location number 1 is going to cause the fluid to receive a force from behind it. So essentially that fluid does some work to increase the speed of the fluid as it moves into that narrow section of the pipe. Lastly, I want to just mention that it was pretty common in Bernoulli's equation problems that we weren't given one of the speeds at one of the locations. And so you need to remember that it's also possible that you may need to use the continuity equation to solve for one of those speeds in order to continue solving the problem. A couple of final points that I think are just worth remembering is first that sometimes we've seen problems where there's been a gauge attached to a pipe that would be measuring the pressure at that location. The way that those gauges work is they use the outside atmospheric pressure and the inside total or absolute pressure, and they find the difference between those two. So if you're ever told about the gauge pressure, you need to know that it's the difference between the absolute pressure inside the pipe, or inside whatever, and the atmospheric pressure on the outside. And so if you were given the gauge pressure, you would need to add atmospheric pressure to that, 1 times 10 to the 5 pascals, or 1 atmosphere, in order to actually know the pressure on the inside of the pipe. Also, we studied Bernoulli's equation by doing a lab in which we filled a 2-liter bottle with water, and water was spewing out of the bottle. And we were able to derive Bernoulli's equation by looking at the relationship between the speed of the fluid coming out of the container and the depth of the fluid in the container. And we found that the speed of the fluid coming out is related to the depth by v equals the square root of 2gh, which was the exact same thing that we learned about the relationship between v and h for conservation of energy for mechanical systems in AP Physics 1. And so, you can study the speed of the fluid coming out by looking at how far it travels on the floor, and so it turns into a projectile motion problem where you can use the kinematic equations to study how that works.